Hello and welcome back. We're going to be jumping right back into the series Introduction into Machine Learning, and in today's video we're going to be talking specifically and answering the question specifically, what is machine learning? Now in the previous video we went over deterministic algorithms and randomized algorithms, and we mentioned how you should try and use one of those algorithms first before looking and seeing if your problem could use machine learning. Now we're actually going to go into, well, what is a machine learning algorithm? And so the first thing you want to think about when you're thinking about a machine learning algorithm is the input and the output. So for the input, you're going to have some input x. The x can be many things that I will get into later, but right now for simplicity, we'll just say that x is a list of some sort of data points. So we have x1 here, x2, x3, and so on. And then for your output, again, we're just going to keep it simple here. Say for every x input, you have one y output. So in this case, the y is, you want to think of y as being the labels for your input, your x training data set. And so when you're looking at what is a machine learning algorithm, you're seeing that there is this training portion involved first. So you first train the algorithm, giving it an x and a y training data set. Then usually, or at least you should, have a test data set, which is just a separate x and y data set. And then finally, you can pass in real world examples. So then you can do real world test. So that's the main point to what is a machine learning algorithm, is when you have some set of data that you feed into the algorithm to train it, then separately you can run other inputs into the algorithm to get specific outputs. So that can be testing it. You give it a bunch of inputs, again, different inputs than your training data set, and you test the algorithm to see how it works. Or you can go on to real world examples where you just maybe pass in one or a few inputs to get one or a few outputs that you then use somewhere else. So that's the main point to what a machine learning algorithm is. You have these three parts of training, testing, and then using it in a real world setting. So what might be some examples of this, of just a bare bones machine learning algorithm with training, testing, and real world? So an example could be as if we have this x and y here, and we want to see, okay, say we know these x data points are on some linear function. So we would know that these data points, so we would have x here and y here. They might be some very obvious, if you plot a lot of these points out, might be very obvious that they are linear. And so we know, okay, a algorithm that you'd want to train it on, it's going over a linear function. So you would only need to do, say, some x sub I times some w equals y sub I. Now in this case, I'm removing, usually when you're having linear equation, you would have some plus b. But in this case, I'm just saying that the y-axis where the function hits the y-axis is at the origin, so 0. So we can forget that extra part. We know that, okay, it's starting at the origin, going up, so we just need to ask what the slope is, or in this case, the w. So, and then these i's here represent each of these numbers 1, 2, 3, and so on. So in this case, the I is just that representation. So in this training portion, we would be giving a bunch of these X and Y values to the training or to the algorithm, and you're going to be wanting to get this W. You're going to want the algorithm to find, okay, what is this W here? What is that very badly drawn straight line? So that's what you want to find. This W or slope for this line here. That then afterwards you can either test it to see, you should test all of your machine learning algorithms before you would actually use them in the real world. But in our case, we'll just say you plot it, you think it looks good, so you don't really need to test it. Your testing is plotting that W and seeing, okay, this line looks like this W line here matches pretty well, so the testing would work. And then you want to pass in some real numbers. So you might say, well, I have this new variable here, or this new input here on the x-axis. What does the prediction look like for this variable? So if we go up to our line here and then go over to a y, the y output would be whatever that point there is on the graph. And that's using that W. So the W is what you trained on. When you were running the algorithm and training it, you were finding that W. Then in a real world test, you gave it an X value and it produced or it predicted a Y value. Now, in a little more abstract maybe idea or a more difficult option or example, I should say here, is what if we have, say, maybe the data looks a little bit more random. You can't quite tell what's going on. It might be a little bit difficult. And you can't even tell, okay, I don't know what function this even is. So in that case, you would want to be finding, well, what is the function of these values though, then? So in that case, you are searching or you're training on this F. So this is where the algorithm now is trying to find this function of X to get Y. And this is actually called, there's an algorithm for this called linear regression. So this is what linear regression is you give it a bunch of X's and Y's, and it creates, or it trains and finds this function, this f of x. And that's what your line is. And say in this case, most likely isn't here, but say it's that line, that's your f of x. So then, okay, you have your f of x. Say we want to find some point here. Again, this is our x and this is our y. Say we have some point here we want to look for, say x sub n, we'll say. You want to find the y value that is associated with this. So you come up to the top here, and then you look and see that was, again, a very bad line, but you get another y sub n. So in this case, you would pass in your x sub n into your function, and that would give you a prediction of some y sub n. Now, just like any other algorithm, you most likely will not have 100% accuracy. You might have random data points. For example, if you go to actually test this x sub n, the actual point for it might be way up here as an outlier. That might happen. But in just finding what this actual algorithm, or going over this algorithm, that's the basis of it. And that's one of these more simpler forms of machine learning algorithms, is something like this algorithm, the linear regression algorithm, where you're just training on finding a function given some x data point for your training and y data points. And so with this in mind, the next question is, okay, that seems fairly simple. So why would we want to not use this? What would this be used for then? Well, generally speaking, machine learning is made for problems that cannot be solved currently with deterministic or randomized algorithms. So that means, say you come up with some problem today. Well, you want to go and look for that problem and see, first, are there any deterministic algorithms that are available for it, or are there any randomized algorithms for it? Now, you might not find any, or you might find some that seem like they might fit, but most likely would not. If you go and try and test it, it would not fit. Once that happens, that's when you move over to machine learning algorithms. So, as I just kind of mentioned, you have some problem you're looking for, say problem A. You first want to try discrete algorithms, and then you want to try I'll just do DA here. You want to try a randomized algorithm, and if both of these do not go through, you find maybe there's some algorithms out there but they don't work, or there's nothing out there for your problem, then you can move over to a machine learning algorithm, or just MA in this case. That's the main point that, at least from the first two videos, you want to take away, is that you do not always want to start with machine learning algorithms. Now, as you get more experience with machine learning, you will notice, and the experience will give you the background knowledge to know when a problem does come up, you'll know right away, oh, this won't work, or there's no discrete algorithm or randomized algorithm for this problem, so I know I need to be going with a machine learning algorithm. And then on top of that, even more experience into machine learning will not only tell you that, but then also say, well, from my past experience, I know this problem might work well with one machine learning algorithm over another. And so that's where more experience will let you go. Okay, now moving on from knowing what a machine learning algorithm is, that it takes some input for training, then you can either test it, or once you're done with testing, move on and pass in real world examples and see how it functions. You know that you should be using discrete algorithms or randomized algorithms first before looking at machine learning algorithms. What's next? So how about some examples of when you could use machine learning and when you should not use machine learning? So here we have 4 different examples that I'm going to walk through. This first one here is just a sorting problem. So we have this list here below, and we want to find a sorted list here. Another problem is a shortest path problem. So we have this graph here, and we want to go from point A to point B. What is the shortest path from point A to point B? Then we have a text to speech problem here. So this is a text to speech. And this could work in the reverse too if you have speech going from speech to text, so audio to text. And then finally we have a clustering problem. So we have a set of data points and we want to cluster them. So these are the 4 examples that we can look at here to see which of these would you think would be best suited for machine learning algorithms and which should not. So going over top left here, we'll start there with sorting. Now you can potentially use a random forest algorithm or decision tree even, or even something reinforcement wise to do some manual sorting of some sort. If you know your numbers are between say 0 and 9, you could try and train a decision tree or train a reinforcement learning algorithm to learn how to sort. You could do that. However, there are already many different ways that you can sort in deterministic time. So for example, there are a few different algorithms for sorting, such as the merge sort. That's one example of a good algorithm for sorting. Another option that's used quite often in programming languages might be something like a quicksort, which uses a few different methods of sorting based off of the size of the input, and so on. There's other different algorithms out there that also work in either deterministic time or random. If you have, say, a large list, or it's a stream, you don't know how large the list is, maybe you could work on random time or randomized algorithms or something like that. That's being said, since there is a deterministic algorithm already for sorting, that just shows that you don't need a machine learning algorithm for it. So with that said, we can safely say that sorting is not for machine learning. So with that done, what about, say, a shortest path algorithm? So we're looking at graphs. Now in this case, again, maybe you could do some going over to reinforcement learning. I know that's my favorite area of machine learning, so I might jump into that quite a bit in my videos. But say maybe reinforcement learning, you can have it find its way through the graph and give it and reinforce it if the path gets shorter and shorter. That could work. However, again, there are already deterministic algorithms for graph shortest path problems. One of them is, say, I'm most likely going to spell this wrong. I always forget how to spell Dijkstra's algorithm. So you have Dijkstra's algorithm is one such shortest path algorithm. Another one could be, say, Prim's algorithm. In which case, maybe if you have weight associated with these edges, you can use one and a different algorithm to say, okay, shortest path based off these weights, or you could just give each path here a weight of 1, and it will just find the shortest path using that one weight. And in this case, you could just pick paths until you find a tree. Now I won't go into detail of that, but that's right there, just two examples of discrete algorithms you can use to solve for shortest path. And again, since we do have a shortest path problem, or since we have some discrete algorithms for this, we know you do not, or not for machine learning. Now, here is where complexity in this next two examples starts to kick up a little bit. Where this is the one thing when you're working with machine learning algorithms, or if you're working with a problem, it's the complexity of the problem is how you can kind of gauge whether you can use machine learning algorithms or not. Usually, if you have a graph, if your problem can be boiled down to a graph, then most likely you can use a discrete or randomized algorithm and be okay, because graphs are very well optimized. However, in these two cases, we have complex problems such as the text-to-speech and clustering. So looking at text-to-speech here, that's pretty complex. You're taking these random-ish, or to a computer, random characters, and you're expecting a specific sound or specific audio being played when those are passed in. So that's a pretty complex problem, and it's so complex even that you may even need to use, say, a neural network for it. So, or NN for short, just because of how complex you're going from single characters all the way to an audio of what those characters should be. So for example, here, if I passed in this text hello there into an algorithm, you would expect the output to actually be say an audio file that says hello there. So in this case, you would want machine learning. So yes, use machine learning. Now, I'm one of the people to say try not to use a neural network when you don't need to. Neural networks should be reserved for the most complex problems, but I will go into that in just a little bit. Moving on to the last problem here in our example, we have clustering. Now for this clustering issue, it depends on what you're asking. So if you're asking, can you cluster these problems, can you cluster this data, and then if I give some data point here, you tell me what cluster it's in, and then from that cluster, give me some output. In that case, you might be using something like a supervised learning algorithm, such as k-nearest neighbors, or if you're just asking the computer saying, hey, I have this data, find me 2 clusters here. And so in that case, you might be using something like k-means, which I will get into both of those in later videos in this series. All these algorithms I'm talking about, I should say, I'm going to go into later, much in depth in later videos. But in this case, depending on your specific clustering problem you're asking, you could do, say, k-means or k-nearest neighbors, which are both machine learning algorithms. Now they're different. One, k-means, is an unsupervised approach. K-nearest neighbors is a supervised learning approach. Again, I will go into those later, but those are all you need to know right now is they are both machine learning algorithms. And so again, this points to yes, use machine learning. And so in this unsupervised approach, say you have with k-means, you might be asking, well, you have those, but what would you be asking for then? In the k-means example, you might be asking, if I have a new data point, what cluster does it actually lie in? So if I have a new data point here, which cluster does it lie in? That could be what you could be asking for. All right, so moving on to something that I alluded to just a little bit ago, is that you should not always want to use the most complicated or complex algorithm when you are looking at your problem. So, for example, neural networks work in a lot of cases. However, there are other less complex algorithms that also work in those cases as well. In that sense, you should always want to look at first what is the least complex algorithm and then work your way up to most complex until you get something that works well enough for your problem. So let's look at an example of that. So say we are going back and we have an X training set and a Y training set, for X being the data points and Y being the labels. And for the X values, say we just have 1, 3, 4, etc. And for the Y, say we have a set like this, where for every X input integer number, you have some Y output integer number that is either 0 or 1. So maybe these X's could be some classification problem, or maybe this is some regression problem that you might want to look at more. So maybe these are, say, 0.73, 1.52, or something like that. I'll say 23. It's like this. So if we have this type of input, what could we look at for possible algorithms to use? Well, let's look at our options here. So depending on if this is a regression algorithm or just simple classification, you might be able to look at linear regression. Another option that you might have available to you is k nearest neighbors. Then you have something like decision tree. And then there might be a few other options available to you, such as an SVM or other algorithms. And then eventually in complexity, we move down to the good old neural network. Now, in this case, I'm trying to move in complexity. So the top part here is least complex. And the bottom here is the most complex. So in this case, as I just mentioned, when you have a problem like this, so in this case we have this training data set we want to train on to be able to get an X input and predict for some Y. You want to use the least complex algorithm first. So you might, in this case, if you decide that yes, this can be solved with some regression, maybe you're trying to solve for some function from X to Y, you can use linear regression, you could try that. And if your input data is a little bit more complex, you actually cannot get a function out of it. Say you have one X value that could potentially have multiple Y values. So it might not work out to be a function that you can actually optimize for. Then, okay, maybe that'll get rid of linear regression. So then you move on and say, okay, well, what's the next next most complex algorithm? So you'd move down and you say, okay, maybe k nearest neighbors could work best. And as I mentioned before, it's a little bit of a type of clustering algorithm. And so it might look, and you could get some sort of accuracy out of this as well. Maybe it's a little bit better than linear regression, or it worked in the first place. And you see, okay, am I happy with the accuracy that I'm getting from k nearest neighbors? And maybe, okay, this isn't the accuracy that I'm looking to get, or it's close, but there's something missing and I can't look into the algorithm a little bit more to figure it out. So then you might move on to something like a decision tree and so on. You would go down this list. And then the last thing you'd want to try is a neural network. Now again, as I mentioned before, some of this will come with experience. The more you work with these machine learning algorithms, you'll be able to eventually be able to look at problems and say, okay, I know this is a fairly complex problem, so we might want to work with some more complex algorithm, maybe gradient boosted random forest, or even possibly neural networks. And for other problems, such as the one we have here, you might be able to see, okay, this is a pretty simple problem. You're just trying to solve for a function. You have this data and you know it can have some function. Well, let's try linear regression first. So that's the biggest thing from this section, is just don't always jump to neural networks. Neural networks and deep learning are kind of catchwords in the machine learning field right now. Yes, they are helpful, but they are not the be-all and end-all for your problems. Just because your problem says, or just because you say you're using a deep neural network for your problem, does not mean it's the best solution. So that's the main thing to think about. And perhaps, say you run a problem, or you have a problem and you actually want to interpret the results. That's something else you also have to think about. Interpreting the results of the algorithm could also be part of your problem that you're looking at. So in this case, say we know what X is, we know what Y, these Y outputs are, but we want to also know, not only have an algorithm to predict for these Ys, but we want to know why it's predicting for that Y value. And so in that case, a neural network would be actually the worst option for you and kind of a last resort if need be, because a neural network is considered a black box. Your data point goes in, or data points for that matter, goes into, say, some neural network, and the output is your prediction, your y. You don't know what's going on inside of this neural network. Just because of all the linear algebra going on inside, there's no way to adequately interpret what's going on. Now, for more complex algorithms, neural networks, you might be able to interpret a few different layers of it. Say for image processing and convolutional layers, you might be able to interpret the hidden layers a little bit here and there to see what the features are trying to learn on. But as for that, there's, as of right now at least, no real efficient way to see why a neural network is predicting the way it is. And in this case, if you know, okay, say in this case you get a data point of 1 and you get an output y prediction of, say, this 1.52, if you train on your data set and say you use a decision tree in this case, the decision tree actually can be shown as a graph, a tree. It is just a tree graph by nature. And so with that, you could just print the tree to some PDF or a PNG file and actually look at and interpret how that prediction was formed. You could start at the root of the tree, work your way down to see what the final prediction became, to see why that prediction is how it was, how the tree came to its conclusion. So that's another thing to also keep important and keep in the back of your mind, is that your algorithms, you should not go for the most complex algorithm. And on top of that, does your problem need to be interpreted? Does the algorithm need to be interpreted to find out what it's doing? So that's just something to think about when you're deciding also what algorithm you want to use here out of this list, or any list really, for any machine learning algorithm. Now to kind of move on to a final point here of what data you might actually be looking at. So I've talked a little bit about X's and Y's inputs. It might be integer, might be whatever. What could your data actually look like? What are the different options for this input? So if you're going to machine learning, you want to maybe think of, okay, I want to have an algorithm that does something specific. What data type should I go and look for? Well, there's a few different, just some examples that I will show here of different types of input data that you could be looking at for any different algorithm that you might run into. So one example just could be pixels. So say even just with the classic MNIST example, it is the MNIST dataset is a dataset of handwritten digits that you can then teach your algorithm to predict. Say if it sees a handwritten digit like that, it should be able to predict the number 5, and so on. And it is a 28 by 28 image, 28 pixels by 28 pixels per image in that dataset. So this could be something that you could be looking for, and it's either filled in or not filled in, and so on. And so that's one option you could be looking at. Another option you could be looking at is, say, just text from anywhere. This could come from, say, books. This could come from internet if you say, scrape Wikipedia, scrape Reddit, Twitter, use any of those public APIs for any of these public websites, you can scrape any of these and see what you might want to get, and so on. So just text. And another option could be, say, just a Boolean value. So you might have yes or no. And in this could be, say, responses to questions. Say you have users that go out and do these surveys, and then you want to, say, take these surveys and have them predict on maybe what their personality is, or if they're more likely to lean one way or another in certain situations. You might have yes or no questions here, and those could be represented as, say, a 0, or not a 0 for yes, you could, but most likely it's 1 for yes and 0 for no, is what you would usually want to use for that. The next is, say, just a floating point value. So, for example, say you're trying to have an input that is some sort of currency. In that case, that's a floating point with 2 digits. And say you have a list of, or a data set of shopping from individuals. So one of those data points might just be how much that shopper spent on a certain visit. So that could just be one example, or another example could be, say, if you took this image example from above and you have these pixels being from, say, 0 to 1, depending on how gray, white, or black they are, then you might have an example like that as well. So that's something else. You might have floating point values. Another option that you might run into is just data points from a graph. So this is a little bit more ambiguous, so to speak, because you might, say, have a bunch of x values here. They could be any part on the graph, similar to what we did for the clustering example that I mentioned earlier, where you might just have a bunch of data points here and so on, and you want to predict a y, or predict, okay, what's the closest cluster that this data point is in, so on. So you might have data points from a graph, and you might represent them as actual data points. You might have, say, 0, 3, and this might be an actual data point in your data set. Or you might be able to represent this as some number. So maybe this is the number 3, because it might be, you do some function over this first number and this second number, and come out with 3 to get that into a different input. Another example of possible inputs, maybe you have latitude and longitude. Say you are predicting where a bird might fly. So you have a bunch of data points for birds of a specific species where they've been seen in the world, and of course those points would be latitude and longitude. And then you might plug those in and say, okay, at this current time, what would be a predicted latitude and longitude? So that could be another one. Again, this might also be considered points on a graph, if you consider the world to be a graph. And it also might be floating point numbers as well. So that's the one thing to note here, is that a lot of your inputs can be calculated and reformatted into other types of inputs. So like I just had an example of turning graph points into a single number, or latitude and longitude into floating point numbers, Boolean values into integers, and so on. But the one thing that you'll most likely see, and you might be able to get kind of an idea of where I'm going with this, is that the majority of your inputs will be able to be boiled down to integers and floats. At the core, a lot of machine learning will boil down to having your inputs and outputs being pre-formatted to being integers or floats, such like neural networks, k-nearest neighbors, linear regression, and so on. Now, some algorithms, like decision trees, do not necessarily need this type of conversion. Decision trees are a nice case where they can work with strings for different inputs and outputs. But generally speaking, if you have some sort of problem that has input and output data, you want to try and get that input and output data formatted down to the most simplistic data type you can. So whether that is working with latitude and longitude data, you want to get that down to specific floating point numbers, possibly. Or if you are working with, say, a Boolean value, convert those to ones and zeros. If you look at a database and it has yes and no values, bring that database down and convert all those yes and no values to ones and zeros. Same with text from a book or the internet. You'll possibly take those words that you see in the text, create some dictionary with them, and have each word being represented as a number. So maybe the in your dictionary might be represented as, say, the number 5 or 530 or something like that. And then from there you can plug in those numbers into your algorithms and you'll be able to learn from them. So with that, in this video we were able to see, okay, what is machine learning? We answered the question, what is machine learning? You're able to take some sort of training data and train on some X and Y values and then be able to pass in individual data points later to get predictions out. You saw that not all the time have algorithms or have problems that need machine learning. You don't always need machine learning. There are cases where you might have discrete or randomized algorithms available for your problem. You also found out that with this machine learning, you want to try and go with the simplest approach first before you move on to the most complex. And then finally, what type of data might you actually be looking at? So in future videos, now that we've gone over actual machine learning, we've gone over data and whatnot, the next thing is going to be going into the different groups of machine learning, such as reinforcement learning, statistical learning, unsupervised, and supervised. So those will be the 4 groups that we will be going over in the future videos, and we'll go more in depth into each one of those groups, looking at different algorithms in those groups and so on. So with that, thank you very much.